Unveiling the Teton Pass landslide and geochemistry and geochronology of the Steen's Monument Dike swarms. Welcome to the GSOG Geology Hour, our monthly gathering of geology enthusiasts brought to you by the Geological Society of the Oregon Country with support from the Bev Vogue PSU Scholarship Fund and the Portland State Department of Geology. I'm Javeria Aziz with co-host Paul Edison Lam. And today we have two very exciting talks for you and lots of questions and conversations. And our presenters today are actually my colleagues here at Portland State University, Lizzet Reyes and Rachel Sweeten. Should we jump right in with Lizzette's talk?
Let's just jump right in with Lizette's talk.
Yeah, so hello, my name is Lizzet Reyes. I'm a master's student at Portland State University. And today I wanted to talk about the Teton Pass landslide that happened a couple of weeks ago. I think it started June 6th, so it's pretty recent news. So today I will be covering the background, the catastrophic landslide itself, some of the causes, and the response and mitigation to the landslide. So the Wyoming Highway 22, it's also known as the Teton Pass Highway, and it is a 17.53 mile long state highway. It spans from Idaho State Highway 33 to the concurrency of the US routes 26, 89, 189, and 191 in Jackson. Around 12,000 people use the road from June to September to reach popular tourist destinations like Grand Teton and Yellowstone National Parks. And it is the only direct link between Jackson and the Idaho communities, where a large portion of the workforce actually lives. So a little bit of the background, the geology of the Teton Pass has steeply dipping sedimentary rocks with slope parallel bedding plains, and it makes it susceptible to mass wasting. There are two inactive geologic structures, the Cache Creek Thrust and the Jackson Thrust, and it runs through the Teton Pass. And the area has competent permeable units juxtaposed against weak impermeable units, which creates a barrier for groundwater infiltration and potential for cliff forming units to be undermined. So the timeline of the landslide, it has been moving for about a quarter inch a year already. But June 6th, there were large cracks that appeared, and that's when it got closed off for a while for it to be patched. However, after that, it started actually moving down the mountain 1 inch every hour, which is a lot of movement for a landslide in that short of a time frame. And then that just kept getting bigger and bigger, those cracks that ended up closing the road. And then the morning of the 7th, it increased to 6 inches every hour. And then further down the road, there was actually a mudslide that occurred at milepost 15. And then Saturday morning, I believe, is when the catastrophic failure happened, and it destroyed the only direct link between Jackson and Idaho communities. So that's what it looked like after the fact. And no one was injured, thankfully. That road was already closed, so there was no one really on it. But it did impact the Jackson residents, where it used to be like a 45-minute drive from Victor to Jackson. Now it is about an hour and 40-minute drive. So it ended up making that commute a lot longer. So some of the causes of the landslide, it's believed that above average snowpack and temperatures in May and June led to intense snowmelt, which increased soil moisture and surface runoff. So the soil saturation from rapid snowmelt due to warmer than average spring temperatures might have led to the increase or the landslide itself. And then the steeply dipping sedimentary rocks with slope parallel bedding planes could have also contributed to the landslide. So financial impact, the preliminary financial impact suggests that Teton County is losing about $6 $600,000 each day that the pass remains closed. That's due to tourism, increased commutes from the county. It also, Teton County depends on at least 2,500 workers who live in Idaho, which is about 15% of the county's total workforce. And how I mentioned this earlier, but the alternate route extends the commute from 45 minutes to about 2 hours. So what are they doing to fix this? Well, there is a temporary detour that is being put in as of right now. It will have a paved roadway with two 12-foot lanes, concrete barriers, and a solid foundation. And it will create a slightly sharper curve and steeper grade with reduced speed limits. This is a short-term fix. They are working on a long-term reconstruction, but there is no timeline for that yet. So this is what the detour looks like. It's going to be on the inside of that curve on the opposite side of the slide path. And that is actually, this detour is actually set to be done by mid next week. So it was a pretty fast response to get that going. They're also working on improving drainage at the slide area where the mudslide happened. There was an emergency bid that was awarded to get that working, and it will help to minimize travel impact. And that's all I have for that. Any questions?
Thank you, Lizzet. That was so interesting. That's actually that whole slide that happened, and then the process that goes into sort of mitigating future slides and then also reconstructing is such an interesting phenomenon. But we'll open the door, the gates for questions. We have one hand raised. Wesley, do you want to unmute yourself and ask your question?
Yeah, I think that's me. The pictures, and even the picture that's on your screen right now, looks like that curve in the road is at the very top of a ridge line. In other words, on the left-hand side, you see the slide. On the right-hand side, it also goes downhill on the other side of the road. Would that have contributed to the proclivity of that area to slide away?
I can see that being a source. Like I said before, this has already been moving for a few years now, and they've been monitoring it. But I think the increased soil saturation really just tipped it over its edge and made that slide go down.
Lizzet, I'll ask a question. Oh, Paul has a question. Sorry, I didn't see your hand, Paul. Go ahead.
Well, I'm always wondering where geologists are working, hopefully behind the scenes to protect us from this sort of stuff, or after to. I mean, I'm seeing the workers who are putting out the cones on as it's slipping down an inch an hour or whatever it was, and I'm wondering at what point are actual geologists involved in the process, both on the government side and then I guess for the construction companies, and what does that work look like?
Yeah, so with the research I was looking at, there are a few head geologists with the Wyoming Department of Transportation that are working directly with them, and they kind of guide the contracts that go in as well. And I'm sure a lot of construction companies also hire geologic consultants to help them. But as far as I've been looking at this, geologists are involved right now, and they're looking at doing a full characteristic assessment of the area to see long-term fixings.
Okay, I have a follow-up question on that.
Yeah.
Where does geology begin and end, and where does engineering begin and end? What's the overlap there?
I think a lot. So the initial investigation, I feel, always goes to the geologists, and we kind of give the suggestions and what we find, and from there usually construction and engineering geologists kind of take over that role and start the designs and kind of the mitigation process. And then after, I think geologists overall kind of oversee it, but it's usually at the start and usually towards the end. That's I think my opinion on that.
Maybe I'll ask a quick question, Lizzet, and then we can move on. So I was super interested when there's a big bend in the road, right, where that landslide was, and
Right.
their idea now, as they did this newer road building, was like narrowing, like not narrowing, but like making a gentler bend. And I wonder if like
This.
yeah, so that's sort of interesting where like why is that just to protect the forest? Like why did they even go out that far out? Is like
So what I read is that there is a specific grade that it's supposed to be at to like reach what is allowed in the state. And so the current detour, because it's not permanent, it's allowed, but that there the grade is too steep for it to be a permanent structure.
that makes a lot of sense.
Yeah.
Awesome. Well, thank you for doing this, Lizzet. This is
Thank you.
super. Maybe we can move on to our next speaker and take it away, Rachel.
All right. Am I off mute? Yes, I am. Hi, how's it going, everybody? A little bit about me. My name is Rachel Sweeten. I'm a PhD student over at Portland State University. I'm also an engineering geologist over at an engineering firm out in Camas, Washington. I've been doing that full time for the better part of 2 years at this point. And I also teach over at Clackamas Community College and Washington State University, and I'm a mother of 3, so I wear a lot of hats. Today, I'm going to be talking to you guys about the geochemistry and geochronology of the Steens and Monument Dike Swarm and the implications and relationships to the magmatic storage of the whole Columbia River basalt group and to the lava flows of the picture gorge and the Steens basalts. All right, so today, like I said, we're looking at the Columbia River Basalt Group. Most of the people, I assume, on this call, since it's the Geologic Society of the Oregon country, I'm pretty sure we've all at least heard of the Columbia River basalts. This is the world's youngest large igneous province, and it was active between 17.2 and 16.0 million years ago. And the bulk of this activity occurred between 17 and 15.5 million years ago. The eruptions were a result of the re-emergence of the Yellowstone hotspot. So originally the Yellowstone hotspot started out in what is now the Pacific Ocean, and it created a large igneous province or an oceanic plateau out there called the Siletz Plateau. And that got accreted onto North America. When that happened, the North American continent overrode Yellowstone. So it had to build up some energy to be able to punch through all that continental crust. And by the time it was able to build up that energy, it was over near where Oregon, Nevada, and Idaho ended up meeting. These eruptions were sourced from 3. Oh, I forgot that I put animations on this. My apologies. During its duration, it erupted about 210,000 cubic kilometers worth of material. To put that in perspective, that goes, as we can see here, that goes all the way from northern Nevada, all the way up to British Columbia, and all the way up to the Pacific Ocean. And we've all driven through the gorge, and we can see how thick it is through there. That is, statistically speaking, a lot of lava. And these were sourced from three main dike swarms, and dikes are these conduits that bring magma from below the ground up to the surface. They're basically the plumbing of the volcanoes. And these were sourced from the Monument Mountain, from the Monument Dike Swarm, which is this orange polygon here with the orange little blebs here in central eastern Oregon. The Steen Dike Swarm, which is within this green rectangle down here in the south, and the Steen's dikes run from Steen's Mountain all the way into northwestern Nevada. And the main bulk of it was the main bulk of the eruptions were sourced through the Chief Joseph Dike Swarm, which is over here within the Blue Mountains and the Wallowas. Today, we're going to be focusing on the Steens and the Monument Mountain Dike Swarm. And our goals for this are we're going to be geochemically classifying the dikes and the other intrusive samples within the study. We're going to use the new geochemical and age data to investigate possible geographic trends with the dikes. And we're going to use that information to determine potential locations for magmatic storage for the Steens and for the Monument and Steens feeder dike systems, as well as try to tie this into the greater Columbia River basalt group as a whole. The project was funded largely as part of a much larger project to study the whole Columbia River basalt group, and this is done in cooperation with Oregon State University, Washington State University, and the University of New Zealand. However, from a practical standpoint, understanding where this magmatic storage is occurring, or where these magma chambers are, to put it in layman's terms, is incredibly important in understanding both the system, both the Columbia River basalt system as a whole, but it's also very important for mineral exploration. Within these magma chambers, these typically host very large deposits, what are considered rook-class deposits, of three main types. These are iron, titanium, and vanadium deposits. Much of the world's titanium, as well as vanadium, which are used in automotive stuff, aircraft, metals, tool steel, things like that. Vanadium is also considered one of our critical minerals, meaning important for green energy transition. We also get copper nickel sulfide deposits, which is where a very large percentage of the world's copper comes from, as well as most of the world's nickel. Our final type of economic deposit that occurs within these magma chambers is what are called platinum group element deposits within a mineral called chromite. And these are between the copper nickel sulfides and these chromite deposits. This is the source of almost all of our platinum group element deposits, and that includes things like platinum, palladium, iridium, osmium, ruthenium, rhodium, and these things are all important, not just from a precious metal standpoint, in the form of jewelry and things like that, but these are also important for the green energy transmission. In fact, everybody uses platinum on a day-to-day basis. If you drive your car, you have a catalytic converter in there, and that's what makes it so that your car is spewing a few less dinosaurs into the air than what it was previously. Which, as we're seeing through the extreme weather changes that have been occurring over the course of the past 5 to 10 years, is an important thing. Furthermore, these magma chambers, when they're in the crust, these act as massive heat engines. So as groundwater is percolating into the crust, it's coming into contact with this magma chamber, and it's getting heated up, and it starts dissolving minerals out of the rocks around it. And these also create their own important deposits, things such as Bonanza gold deposits, Carlin gold deposits, and these are the source of much of Nevada's mineral wealth. And last but not least, these magma chambers also start melting pockets of crust that lie above them and near their edges. And these create these massive calderas, or these rhyolitic eruptions that some of the other speakers that have been part of this group have talked about. And these massive calderas are sources for many other critical elements, such as lithium. As people here might be aware of, we actually have a lithium mine starting up down in McDermott, in the McDermott caldera, which is actually very close to Steen's Mountain, and the magmatic storage from the Steen's basalt is part of what created that deposit. So understanding where these magma chambers are is of critical importance. So without further ado, let's go ahead and continue. So first, we're going to go ahead and look at the picture gorge basalts. You guys heard from a previous speaker, Emily Teton, a bit about it. So we'll go ahead and recap some of the information. So the picture gorge basalt is the smallest main phase unit, with the eruptive activity occurring between 17.2 and 15.8 million years ago, according to Teton et al. And like I said, this was the smallest of the main phase eruptions, and only erupted between 3 and 8,000 cubic kilometers worth of material. However, it erupted at over a very wide area, as research by Teton has determined. Now, geochemically, we can classify these picture gorge basalts in 3 different geochemical subunits. And these are in order of age from youngest to oldest. The day built a monument mountain, the Twickenham subunits. And with the extent of these, originally they were thought to have only occurred around the John Day Monument Kimberley region. However, work by Teton has actually determined that we can see PGV type basalts as far east as Sucker Creek, Oregon, as far south as Hart Mountains, and all the way out as far west as Pineville. So these are actually a much larger footprint than was originally assumed. And this part's going to be important later on in the talk. Secondly, we also looked at the Steen's basalt. The Steen's was as one night last night. The eruptive activity of the Steens occurred for about 17 million to 16.5 million years ago. However, Steen's type lavas have erupted not just within the Steens area, but within much of the region of the Oregon-Idaho province, approximately south of the Snake River Plain. The vast majority of the CRV lavas that have been erupted in that region are all Steens type lavas. However, we are familiar with Steens based off of Steens Mountain. However, these lavas encompass a much, much larger area than just that. And most of these were sourced from dikes running along the Steens Escarpment, going south all the way into northern Nevada. The Steens also has 3 geochemical subunits, and these are defined by Mickey Moore as the upper Steens, which is the youngest unit, the lower B Steens, which is the middle unit, the lower A Steens, which is the oldest unit. And activity within the Steens region began as fissure eruptions near the Oregon-Nevada border and progressively moved farther north until it became centralized around Steens Mountain. And once it became centralized, it started building up the shield volcano that we now know as Steens Mountain. But like I said, Steens type lavas have erupted as far south as central Nevada, and have erupted as far east as the Santa Rosa Calico volcanic field, which is very firmly on the Nevada-Idaho border. So again, these are very widespread, even though the dike system is only exposed in one small area. And Steens Mountain, when that activity centralized, Steens Mountain was erupted virtually continuously. It was nonstop eruptions, similar to what we're seeing in Iceland today. With the, I can't pronounce the name, but we've all seen it on the news, over near the Reykjanes Peninsula. So this thing was active near constantly with long lava flows, very similar to what you would see in Hawaii, where you these long, thin, ropey, very long flowing, what are called basalt flows. So to understand where storage and all of that might occur, we also need to understand not just the CRVs themselves, but we also need to understand the geologic setting that these are in. So the bedrock geology of the area is going to be consisting almost entirely Mesozoic and Paleozoic treated terrains, and overlying those, we've got widespread Eocene and Oligocene volcanic deposits, as well as rhyolitic deposits that are occurring at the same time as all of these basalt eruptions. Remember, as I said at the beginning of the talk, when we start getting magma chambers forming, well, they start causing pockets of crust nearby to melt and explode. And that's our felsic eruptions that we see in the area, things like McDermott caldera, the Strawberry volcanics. All of that stuff is created by the presence of these magma chambers within the crust. We also have some quite a few structural components. And when I say structure, I mean things like faults and boundaries between major geologic units. But in this case, I'm going to focus a little more on faults, specifically the normal faults. And we have several components. We've got basin and range extension to the south of the Oregon-Idaho province, which is this region right here. I hope everybody can see the mouse. Which is this region right here. And so south of the Snake River Plain and south of the Oregon-Idaho province, we have what's called basin and range extension, which are these normal faults that are extending because the Pacific plate is subducting underneath Alaska and it's pulling apart North America and starting from Baja California and going all the way north up into this spot. So we get these extensional faults that occur because of that. We also have extension because of rotation of the cascade block. So again, because of this, what's called orthogonal subduction, we are seeing where the cascades are starting to pull away from where they're currently located at and rotating around a point up in central or near the Oregon-Washington border, up near close to Pendleton. And so that causes northwest striking normal fault zones that also have a dip slip component to them. So they're extending and dropping down from one another, but they're also sliding by one another. And that's going to be things like the Eugene-Daniel fault zone, the Brothers fault zone, and some of the Harney Basin fault lineaments that appear. We also get things like the Western Idaho Shear Zone, which runs along the 706 Strontium line, and that's where all these accreted terrains docked against the North American continent during the Cretaceous. And so we've got a lot of structural components, and this is important because just like any other fluid, as magma's rising through the crust, the places where it's going to be stored is places where it doesn't have a clear path to get to the surface. So these are going to be what are called traps, kind of like the U-bend in your sink where it traps the gas in there. And we see these kinds of traps occur in several different types of places. Just speaking in a generalistic sense, we see these traps can appear in discontinuities between major geologic units or minor geologic units. They can occur along fault lines, and they can inject in between different stratigraphic units within basins. So understanding the geology of the area and understanding the bedrock geology of the area and the structure of the area allows us to get a good idea of the various paths that these magmas can follow. All right, so let's go ahead and look at the picture gorge dikes. So age ranges of all of our sampled intrusives are all in agreement with the extended time frame of the picture gorge basalts that were established by Cahoon in 2020. And our work shows that the system was actually active from about 17.27 million years through to about 15.61 million years. And this actually encompasses the entirety of the duration of the main phase of the Columbia River basalt volcanism. These dikes generally intrude through Baker and icy terrain rocks south of US 395. And north of that, they're intruding through John Day and Carno volcanics. We were also within the John Day and Carno volcanic region. We were also able to find several sills. So to kind of give everybody a little bit of a sense here, dikes are generally are vertical conduits for magma to travel. So these are vertical pipes that they're traveling physically up through the crust. Sills are horizontal, so one's going up and one's going sideways, basically. And the sills are the ones that go sideways. Sills can turn into magma chambers, as can dikes, but most of the time we see sills typically turn into magma chambers. These sills were a couple tens of meters in thickness, so anywhere between about 30 to about 100 feet thick. And they have zones of alteration around them, but they're not very long-lasting alteration. And when I say alteration, I mean as these are intruding into the crust and heating things up, first they remove things out of the rocks around them, things like potassium, iron, calcium, and things like that, stuff that is able to be dissolved in water and pulled out of the rocks that are surrounding them. When things sit there for a long period of time and then cool over a long period of time, we see what's called mineralization. So alteration is removing stuff from the rocks, and mineralization is redepositing new stuff into the rocks, things like chalcedony, things like agates, jasper, stuff like sulfide minerals, like boronite, which is peacock ore, iron sulfide, or fool's gold, copper sulfides, and things like that. So just to give everybody an idea, when I say alteration, I mean where it's removing stuff from the rocks, where it's turning it into clays and things like that. And we see around these sills where it's had alteration, but there's no mineralization that's occurred. So there's no mineral deposits that are nearby, just it's basically baked, the stuff that's directly above it. These dikes were generally striking between about 300 and 330 degrees. So between northwest and north-northwest, approximately in direction. And this parallels normal faults within the region. Not only that, every single solitary dike that was sampled within the monument dike swarm, there is a normal fault that strikes the exact same direction within a kilometer or less of every single solitary dike. So that tells us something important. That tells us that the dikes were using normal faults, not discontinuities between different geologic units, not different, different layers between stratigraphic units, but it tells us that the dikes were using normal faulting to be able to travel from point A to point B, and these were most likely going to be the spots where we'll find potential storage at. Another interesting thing is the dike widths in the Monument Mountain region range between fairly narrow, with some dikes only 2 or 3 meters wide, or about 6 feet wide. But the vast majority of the dikes are actually very thick, up to about 7 to 10 meters wide, so about 20 to 30 feet wide. And in some cases, there were 2 or 3 that were almost up to 100 feet wide, or about 30 meters in length, which is huge. That means that these were not just small conduits transferring magma from point A to point B, but these were actually huge conduits. And we also notice that the alteration halos around these dikes are actually fairly small. So that means that not only is it transferring a lot of rock or a lot of magma from point A to point B fairly fast, but it's also not sitting there for very long, which is important when we're looking for where these things are getting stored. However, it was noted that when these dikes were passing through terrain rocks, they actually had much larger crystals, which means that they did have a little bit longer cooling time than the stuff that we see in the John Day Basin to the north. So when we look at it from a geochemical perspective, we see a couple of very interesting things pop out. Dikes that were classified as Monument and Twickenham all seem to form one singular trend, starting within the basalt field here, and then staying almost entirely within the basalt field, with only a few samples of Monument Mountain actually trending into basaltic andesites. That means that most of these magmas were fairly primitive, and they most likely did not sit on the crust for a long period of time, because we would see more basaltic andesites and things that have more continental crustal contamination. We also see that Dayville, while it initially starts out as more depleted than Twickenham and Monument Mountain groups, we see that it very quickly evolves into much more enriched, both in alkali metal, or in the alkali metals of sodium and potassium, but in almost every other trace element that we have as well. When we look at our trace element and rare earth diagrams, so the trace element diagrams are the diagrams that are on the left-hand side here, and the rare earth element diagrams are the ones on the right-hand side. All these units, when we look at both of these diagrams, show what's considered a fairly depleted trend. If we notice, other than the spiky bits here, these are fairly flat. And what this tells us that this is very similar to what's called mid-ocean ridge basalt, or a very depleted basalt. However, when we look at our trace element diagram over on the left-hand side, we can see that the fluid mobile elements are very enriched, much like what we would see with the Cascade Arc. So what this means is that these are coming from a mantle that is relatively depleted. However, it's seen subduction, which follows, it follows what we kind of know about the area. It's been experiencing subduction since the Mesozoic. So we would expect to see that, and that's not really news. However, when we look over at the rare earth diagram, we can actually see that Twickenham and Monument Mountain have something called a europium anomaly. So what this means is that instead of staying in line with the trend that we see here, we see that the europium values are actually a little higher than that trend for Monument Mountain and Twickenham. However, we don't see the same thing in Dayville. And again, this is going to be something that becomes important later on in our discussion. Well, we're looking at some comparison diagrams. We can also see, again, Monument Mountain and Twickenham plot either within the same fields or as part of the same trend, and Dayville plots as its own trend. And I kept the colors consistent through here. The Twickenham and Monument Mountain are going to be purple and blue, and the Dayville dikes and flows are all going to be that salmon pink. And the samples that don't really classify well because they have too high magnesium in them are labeled as the high MgO samples. And something that's really interesting is this diagram here. This is a mantle discrimination diagram. And what we can see is that it looks like Monument Mountain and Twickenham come from a different mantle source than the Dayville flows. So moving on to Steens, the dikes, the Steens basalts largely follow trends that were established by Camp, the ones that I discussed earlier, where we see fissure eruptions begin on the Oregon-Nevada border and progressively get younger as they move farther north, and then centralize here at Steens Mountain. Overall, the dikes at Steens Mountain were in general much, much smaller than what we saw over within the Monument dike swarm. The vast majority of the dikes sampled in Steens were only about 2 to 3 meters wide, so about 6 to 10 feet wide. But once you get closer to Steens Mountain, some of these dikes started getting up to about 30 to 60 feet wide. As you can see in this picture here down at the bottom, this ridge line going on the right-hand side is a much, much bigger dike than the one on the left-hand side, but they're both dikes associated with the Steens dike swarm. Another interesting thing is we see a very, very large zone of alteration that begins near the southern portion of Steens Mountain along what's called Catlow Valley Road, which is this nice little valley that cuts right through the Steens area. This is a strike slip or dip slip fault zone, very similar to the fault zone, and parallels this. And we see this zone of alteration and mineralization going from the Catlow Valley Road all the way to south into northern Nevada to south of Denio. And well, this would indicate that there's long-term storage within the region, which leads right into our next slide. The discovery of the Lady Cone layered mafic intrusion. Now, layered mafic intrusions are long-lived magma chambers, and they form a layering of minerals based off of the convective chamber, the convective current that begins in the magma chamber, and it starts winnowing out the minerals by density as they're crystallizing out. So some of the people here are familiar with the Bowen's reactions theory. So if you start with high temperature, you get very specific minerals that crystallize out, specifically olivine, high calcium pyroxenes, and high calcium plagioclase. And all of these have got different densities. So as this is convecting, the heavier minerals start dropping out closer to the bottom of the chamber, and the lighter minerals float to the top of the chamber, and it starts creating this stratified magma chamber where you have what's called anorthosite, which is a rock composed almost entirely of plagioclase, and then you get layering where you get progressively more primitive layers that increase in both olivine and or pyroxene as you go farther down the chamber. And at the very bottom of the chambers, oftentimes you will find what are called copper nickel sulfides, because as the sulfide minerals reach a certain point within the magma chamber where they reach tipping point, the magma cannot hold any more sulfur dissolved within it, and it all precipitates out. And it is these liquid sulfides are significantly heavier than any other mineral within the chamber. To put it in perspective, olivine is like 3 grams per cubic centimeter, but sulfide minerals are like 9 to 16 grams per cubic centimeter, and they're much more fluid. So they sink to the very bottom of the chamber, and you'll have sulfides down at the bottom, and then a olivine layer that's called a dunite. And then you get things where you start getting mixes of some minerals or one or two minerals, and then single minerals by themselves like chromites, and so on and so forth. And understanding the layering of these chambers gives us a good idea of, how it evolved and so on and so forth. Now, the geochemistry of this layered intrusion indicates that we have a potential iron, titanium, vanadium resource located within the top of the chamber. And the mineralized deposits that are by this region, especially both to the extreme north and to the extreme south of how far this extends, also show indications that it is very copper enriched, which would indicate a copper nickel sulfide. We can also tell by stratigraphic relationships and between the Steen's basalt flows and what's called the country rock or the host rock that predates all of this stuff. As well as dikes associated with this, Steens. We can tell that this is definitely Steen's age, and this makes this the very first. This makes it the very first and only layered mafic intrusion that's ever been discovered with the Columbia basalt group. As I mentioned at the beginning of the talk, these things are incredibly important from an economic perspective, and also incredibly important in understanding the evolution of the Columbia basalts as a whole. And this is just kind of a teaser about it, because this is actually what I'm focusing my dissertation research on. So when we look at the geochemistry of the Steen's basalt, we see that things basically line up to what was already classified by Moore and Camp and a bunch of other workers previous to that. And what we see is that the occupies both the very primitive and the very evolved ends of the compositional spectrum, both in the trace elements and in major elements. Lower B samples are almost entirely very primitive, and upper Steed samples are almost entirely very evolved and crustally contaminated. And what this indicates is, and this is a classic pattern that shows up as you're developing magmatic storage. Your very first initial eruptions are either stall out in crust and evolve a whole bunch, or incorporate a whole bunch of melted crust into them and become very evolved, or it just shoots straight to the surface from the mantle and you get something that's very primitive. But once you have storage established, and you start developing a vigorous volcanic system, well, it starts recharging as fast as the chamber empties. So we start seeing almost entirely primitive geochemistry showing up. And then as the magma chamber is starting to slow down and wane, as the activity is moving away from it, we start to see the magma sitting in the crust longer, so it becomes more evolved and also has more signs and signals of crustal contamination, because as it sits in the crust longer, it's melting the stuff around it, because the stuff is really, really hot. And well, as it's melting the stuff around it, well, it mixes. And so it starts developing a much more evolved chemistry, and also chemistry that contains things, much more things like potassium, for example. And so as far as things go, like I said, nothing major new was discovered in the form of the geochemistry, but what we did find aligns directly with what Moore et al. had discovered, which is that we do see these three very specific stages showing up. So now, bringing this together, when we look at when we start looking at the picture Gorge system, what was becoming very abundantly clear is that we actually have two very distinct trends, not three. And as such, we should actually just classify this as two trends and not three trends. My thesis research proposes that we simplify the stratigraphy of picture Gorge basalt into two geochemical subunits: the Twickenham subunit, which encompasses the original Twickenham subunit, as well as the Monument Mountain subunit, and the Dayville subunit. And when we do that, we can see that we have two very distinct magmas. And when we start plotting them out on various discrimination diagrams, and most of the ones that you see on your screen are different mantle discrimination diagrams. And we could see that not only are these different magmas, but they come from different a different source. Now, if we look at the right, we can kind of pick that apart a little bit, and we can see on our x-axis, this gives us the ratio between lanthanum and terbium, give us our ratio of partial melting. So, as your mantle is heating up, you start melting incrementally. It doesn't instantaneously melt, or at least not generally, unless something instantaneous happens that causes melting. You normally incrementally melt. And the y-axis, or the vertical axis, the terbium diagram, gives us an idea of the measure of the amount of garnet that's within the mantle. So it tells us not necessarily the location, but it tells us at least qualitatively that these are different mantle types. And what we can see here is that we can see that the Twickenham subunit is in a mantle type that has between 2 and 5% garnet, and almost exclusively it is almost exclusively between 5 and 10% partial melting. And the Dayville subunit, on the other hand, comes from a fairly garnet depleted mantle, where it's only got between about 0 and 2%, maybe is up to as high as 3% garnet. But it covers this wide range of partial melts, and this actually tells us something very important. Not only are these from two very different mantle sources, but these also have two very different processes associated with the two of them that were causing these melts and therefore these eruptions. We see with Dayville, it has a fairly constant garnet amount, but the partial melting changes over time. And that's something that we would expect to see when we have hotspot influencing things. As that hotspot is getting closer and closer to the surface, and that heat is influencing things around it, we would expect things to melt slowly over time and until it hits a certain equilibrium point. However, what we see with the Twickenham subunit is that it's got a very narrow range, which means that there has to be something very specific occurring to cause it to melt within that very specific window. And what that would mean is that there's a tectonic control causing the mantle to depressurize and melt at a specific percent. This would align with what's called the difference between active rifting, where you have a anomalous heat source, whether it be a very, very hot mantle or a hot spot, causing incremental melting around it, or what's called passive rifting, where the act of spreading apart is lowering the pressure on the mantle and therefore lowering the temperature that's needed to melt that portion of the mantle. So it tells us that Twickenham is most likely tectonically controlled or rifting controlled. So as that hot spot is pushing up on the crust, it's causing the crust to extend. And so every time it pulses and fills up that main magma chamber base of the lower crust, it's causing some spreading to occur. And every time it causes spreading to occur, it causes melting and therefore Twickenham eruptions. Whereas the Dayville eruptions are being caused by the fact that that hot spot, as it's coming to the surface, is slowly heating the mantle around it and causing those eruptions. So to take a look at the magma storage and transport, we should recap a few things. We know that the Twickenham and the Dayville subunits have got different mantle sources. Different mantle sources means, obviously, different storage systems. We also know through work done by Wolf et al. That the Naha and the Grand Ronde phase units are also part of the same mantles, or part of their own mantle source system. We also know through Brusecki and Camp that the Santa Rosa Calico volcanic field, as well as the Northern Nevada Rift, those magmas share chemistry with Steens, and for simplicity's sake, we're going to consider those Steens magmas and consider that those come from their own source. So by this, we have 4 different sources, or at least 4 different main locations to look for magma chambers. We also know that these coeval felsic magma chambers, these rhyolitic eruptions that form, these are buoyancy filters to the ascending basalt. So as the basalt's rising, part of the reason why it's rising is because it's more buoyant than the crust that's around it. But basalt is not more buoyant than a hot rhyolite. So when it hits those hot rhyolites, it stops. It can't go any further unless the rhyolite moves out of the way. So we know when we're looking at storage, the outer edge of our storage show line with what we're seeing for these explosive eruptions. We also know that a long-term storage system should create a very robust hydrothermal system. And not just robust, but we should also see base and precious metal deposits. And we see very specific deposits that show up around these mafic intrusions in Nevada in the form of bonanza gold deposits, or what are termed as bonanza deposits, such as the Sleeper Mine in northern Nevada, as well as part of the Carlin, what are called Carlin gold deposits that form on the Battle Mountain Eureka Trend in northern to central Nevada. And the vast majority of Nevada's gold comes from that region, which directly overlies the northern Nevada rift system. And work done by several others is directly linked the gold through isotope data to Steen's basalts. So we know that when these intrude into the crust, we see very specific types of deposits that form. And north of the Snake River Plain, we see something called skarn deposits. So as these things are these hydrothermal fluids are rising up, they're very, very acidic. And when they encounter the calcium or the limestone deposit known as the Martin Bridge limestone within the Wallowa region, they instantaneously neutralize. When they neutralize, they drop all of those base and precious metals around them. And these are what are called skarn deposits. So when we look at a map, when we plot out all instances of mineralization on the map, and we filter those for the types of mineralization we would expect to see, that information can also provide us clues as to where this magmatic storage is occurring. And we see very minimal evidence of storage within the Monument Mountain, or within the Monument John Day region. So that also tells us that not only were the pictured Gorge basalt sourced from two separate chambers, but these two separate chambers were not within picture Gorge. They were actually sourced from farther away. So this starts giving us some parameters where we're going to find these. And last but not least, we should also see what are called gravity anomalies, specifically isostatic gravity anomalies. These magma chambers are going to be formed of minerals that are much denser than the crust around them. So we should see these as a positive isostatic gravity anomaly. Furthermore, as things are crystallizing in the chamber, those two of those three main deposits that I mentioned that can form within these iron, titanium, vanadium deposits and copper nickel massive sulfide deposits will also contain an extremely strong positive aeromagnetic anomaly. So locations where we see aeromagnetic anomalies, positive aeromagnetic anomalies, positive isostatic gravity anomalies, and mineral deposits that are within the envelope created by these rhyolitic eruptions, and show a clear pathway that goes from these anomalies to the eruptive locations. Well, by process of elimination, these must be our locations for our magma storage. And what we see here is putting all that information together, we come up with this model here. We can see that the storage from the Anaha and the Grand Ronde basalts occur north of the Highlock Plain, Snake River Plain fault lineament. We can see that Twickenham was sourced from some small magma chambers within the western Snake River Plain, with some potential overlap with the Twickenham magma chamber, with the Dayville magma chambers. We can see that Dayville was sourced from the northeastern Harney Basin and was transported to the Monument Mountain region through the central Harney Basin and eastern Harney Basin fault lineaments. And we can see that the bulk majority of the Steen's magma was stored within the orgonite graben. And it looks like I need to hurry up because I'm starting to see Barry and Paul pop up.
Yeah, I was just going to give you like a quick time warning so we can start wrapping things up.
My next slide is the conclusion. So we're
Awesome.
almost
Thank you,
there.
Rachel.
All right. So in conclusion, this work, we were able to sample 48 new dikes and several small sills for the monument dike swarm. We sampled 26 new dikes and 1 layered mafic intrusion for the Steen's dike swarm. We've got 10 new age dates for the monument dike swarm. We were able to simplify the geochemical designations for the picture Gorge Basalt into 2 compositional subunits. And last but not least, but certainly I feel most important, we discovered the first and only layered mafic intrusion exposed with a collective assault group, and this is related to the Steen's Mountain main phase unit. And this new intrusive data was integrated with all the available geochemical, geophysical, and geographic data to create a model of Columbia River basalt cruising upper crustal storage locations. All right, any questions?
Thank you, Rachel. This is so great, and it's been in such good detail that you told us about all this stuff. And I'm personally super excited about the work that you're continuing to do. So thanks for sharing that, and we're all looking forward to all the amazing work that you're going to be doing now with your new grant. So congratulations on that.
Thank you.
Does anybody have a question? If you have a question, you can write it down in the chat, or you can raise your hand and ask your question directly. But we have time for maybe like a quick question, and then we can wrap this up.
I don't see hands raised.
Yeah, I don't see anything yet also. I think people need some time to process this information. I loved all the geochemistry that you talked about here. All right, so sorry, go ahead, Rachel.
Oh, I was going to say I tried to make it a little more digestible for the layperson. The petrology stuff can get a little complicated, even for those of us that deal with it on a day-to-day basis. So
totally,
yeah.
Yeah, I love the comment by Alexander Gordon saying wonderfully overwhelming.
It certainly felt that way when I was doing all of the research. Masters typically take between 2 to 3 years, and this one took 4. But I like to adhere to the Ron Swanson ethos of, to paraphrase, why do something half-assed if you can do it whole-ass? Pardon my French.
No,
totally. I mean, you did a PhD level work for your master's, and now you're doing a second PhD. So that's incredibly impressive in itself.
That was my question. So, is Rachel, will your PhD continue on this work?
Absolutely. So my PhD is going to start by focusing on that layered mafic intrusion that was discovered and going through and kind of determining the geochemical evolution of the chamber, how it relates to, the Steen's basalt and the CRVs as a whole. But also, I feel a little more importantly, I'm also going to be doing what's called resource valuation on the chamber. So determining the amount of the iron, titanium, vanadium resource there, its current market value, as well as any other potential metals that are within that region that are caused by this layered intrusion. And then finally, I'm going to take all of the information that I synthesized from this and apply it to other locations within the region to see if there are other possible layered mafic intrusions that are exposed that just haven't been discovered yet. Basically, I'm using this as an excuse to take my G4 wheeling into very remote areas and getting paid for it.
Rachel, we do have one question, and maybe you can answer this quickly. It's in the chat, we have a question from John saying, is there any chemical signature that ties the mantle source to the crescent formation to connect the Siletz terrain?
There is, but that wasn't a focus of my research. That's something that has been focused on by, I'd like to say, Emily Capoon, as well as Victor Camp, Ray Wells, and a few others. There's certain chemical signatures that are shared by all hotspots. This is called what's called ocean island basalt. And that forms a very characteristic trace element pattern. And we could, combined with tracing the hotspot motion back, we can see that the Siletz basalts share that same ocean island basalt pattern and also fall within the projected Yellowstone hotspot track. And that ocean island basalt is very different than what we would see at a mid-ocean ridge or at, like, say, for example, the Cascade volcano. So it kind of gives us at least some kind of fingerprint to go, this certainly came from a hotspot. And since Yellowstone is the only hotspot around, well, you know, the simplest solution is often the correct one.
Yeah, I believe there's, if I remember correctly, there's a Wells and Camp paper that talks about it. It talks about the Siletzia being the impingement phase of the Yellowstone plume. It'd be an interesting read, John. Awesome. Well, thank you, Rachel. Thanks for doing this, and thank you, Lizzet, for being our first speaker.